Hello and welcome to Leibniz. Today we're starting our first series on calculus. Now, calculus is one of my favorite topics since it is used to solve such a variety of questions. I think it's just such an interesting way to go about abstract maths from your basic algebra and geometry. Now, if you're a STEM major, you're doing anything related to the STEM fields or just have an interest in it at all, it is exceptionally useful in order to solve the sorts of problems that you would come across in the real world, that you're analyzing things in engineering or in physics or in the technology that you'd be producing. In all sorts of fields, it is amazing what it can do. Now, the story of calculus starts several hundred years ago with a group of mathematicians who all had a general idea of wanting to try something new. Now, geometry and algebra had been around for thousands of years by that point. I mean, the Greeks were doing it back in the BCs. Now, calculus is the idea of using infinitesimally small portions of sums in order to approach smooth curves. Now, if that doesn't make sense right now, don't worry. We will derive calculus in the same way that its original founders tried to do. And we'll try and make it a little bit more intuitive using some visuals and some of the derivations that they used originally in some more modern terms. Now, a lot of people had the idea of calculus, or something along its lines, for quite a long time, but the two people most famous for formalizing it are Newton and Leibniz. Now, there are a lot of questions that mathematicians and physicists and engineers have been asking about the real world that algebra and geometry can't really handle. For example, how do you approximate smooth curves very, very accurately using only straight lines? You can do it. It's a little bit difficult. For engineering, it can work for small-scale technologies. But if you really want exact answers or proofs that are very exact in the way that Isaac Newton needed, you need the idea of calculus to take things to be infinitely precise in order to make your answers exact. We'll cover that in the next video about limits. Now, if you have already started a calculus course, if you have some familiarity with it, I know that might seem a little bit scary. We will try our best in order to bring up the idea of what derivatives and integrals are first, which are the two main pillars of calculus, without necessarily requiring the limits. We'll still go over them, we'll do some practice problems, we'll learn the basics ways to use those things, but we want to share with you the best way to go about learning derivatives and integrals in a way that makes sense, instead of it all being abstract mathematical jargon. So, as a basic introduction, a derivative is simply a generalized slope. That you have your y equals mx plus b that you learned in secondary or middle school. That is the straight line approximation of a slope that you could do for any flat line. But as soon as you want to do that with curves, a derivative is exceptionally useful because it can find that slope at any point along any curve. Now, an integral can do something similar, except instead of finding the slope, it can find the area contained within that curve, both of which are exceptionally useful when dealing with objects like this in the real world that are curvy and have these smooth, rounded edges on them. In this series, we'll be reviewing both of the fundamental pillars of calculus, the derivative and the integral, as well as two other topics that are usually taught in classes, such as calculus A, B, or BC, where we have limits and sequences/series. Now, limits are really useful for the abstract mathematical derivation of a derivative and an integral, and it makes much more sense as an idea, as a concept, than it does the actual abstract mathematics. But we will go over both just so that you can have both the conceptual understanding as well as the ability to do your homework problems. For sequences and series, that's a bit of a more advanced topic later down the line. We'll cover that after we've done the derivative and the integral sections so that you can have the experience of both of them going into the sequences and series, which is usually covered at the end of the course anyway. Thank Thank you for watching. Hope you see you around.